Yeah, thanks, Lava. So as he said, the title of my talk is A Practical Guide to Mathematical Tools, or Linear Regression. And I've given it the subtitle of The Unsung Hero of Machine Learning. Before we begin, a couple of quick disclosures. If my advances will work, mouse it is. So I am an independent consultant. Just to be clear, these are my opinions and should not be taken as representing any client or company with whom I have relationships. This is just me talking in a pretty much informal fashion about my experiences as a data scientist. I can't see chat while this is happening, but feel free to use the Q&A function, and there's a Slack channel to talk about any questions or discussions you may want to have about this talk or in general. So about me personally, for those of you who don't know me, I tried to make my career kind of on the boundary between technical fields and business. I have a PhD in electrical engineering from the technical side and then a master's in business administration. And I have 20 years experience in industry, but that's a variety of industries, including defense work in the US, biomedical engineering here in Australia, and banking primarily in risk. And those might seem quite disparate in terms of the skills I would need and everything else. But upon reflection, what I enjoy the most is implementing systems. So when I was in defense, actually going and being a part of flight tests to see my work in real time. Patient trials for biomedical engineering. I was on the Bionic Vision Australia project, and the mathematics and the programming and everything was great, but there's something to knowing that you wrote code that is driving an implant so that people can perceive. So I can literally say that I've worked in bringing sight to the blind. And then in banking or risk, you're assessing customers, the bank's profitability, their capital levels are due to things that I've created, and I find that really fulfilling. So my goal is to have a measurable impact. I don't necessarily care if I'm using the latest and greatest tools on the cloud environments with all the fancy bells and whistles. At the end of the day, I want to see the fruits of my labor and to know that I've had a measurable impact in whatever models I build. So for the goals for this presentation, the primary audience I've built this for is industry non-specialists. So programmers, architects, managers. Secondary is business analysts or junior analysts. Although that said, you might find the math a little easy. Bear with me. I'm going to start off with a general introduction to linear regression. Talks about scalar linear regression or simple linear regression, talk about linear algebra and some matrices, and then the calculations involved. The primary focus of this talk, though, is these practical approaches. So while I will discuss the mathematics of linear regression, what I want to focus on is what are the related concepts, what are some auxiliary tools that linear regression gives you, and to go through that with an example problem. So let's start off with simple linear regression. Basic stuff, right? My assumptions here is that you have some variables. You have a single scalar independent variable, single x value, and a single dependent variable, a y value. And I have a number of them. So I have all of my different x values and their corresponding y values all taken together. And they're both continuous. So it's not a classification problem, it's a regression problem. And what I'm assuming is that the mean of my my dependent variables, my y values, can be written as a linear function of all of my independent variables. So for every observation I, the expected value of that observation is some constant plus a multiple of my independent variable x. But my individual measurements, my individual y values are all noisy due to some error term epsilon I. And from here, we see one of the big factors when you're starting to build a model is that I'm saying I will not know my outcomes perfectly. There will always be a bit of noise at the end of it. And in typical fashion, you assume that these errors are independent and identically distributed with mean 0 and variance sigma squared. And what I'm going to try to do with my linear regression is to find estimates of these intercepts and slopes. In general, when I have that little hat, that means I have an estimate. So I'm going to have y hat, or predicted value of y, such that I minimize the total sum of squares. If I look at all of my y values and all of my predictions, I take the difference of all of those, square it, add that up, And I want to find C0, the constant, and C1, the slope, that minimize that sum. So here we have something that, if you're used to kind of doing things by rote, seems a bit odd, that now X and Y are inputs, and I'm trying to solve for C0 and C1. If I go through an example here, I have X and Y, and I've got a scatter plot of data. And something that's nice about simple linear regression is if I give this to you and say, come up with a function that fits this, you could fit a line. You could just take some time and look at it and put a line to it. Now, if you look at it slightly differently from a different perspective, you might see that line wobbles. So if I give this to 20 people on transparencies, if you remember transparencies, and stack them all up on each other, you'd often see a little bit of a wobble in this line. And note that if I increase the slope coming up, the intercept goes down. And if I increase the intercept, the slope goes down. So there's this correlation or inverse correlation between my two parameters, that if I change the slope, that tends to change the intercept. If I change the intercept, that tends to change the slope. So after you've gone through and done that by eye, you can calculate the optimal line. Why is this line optimal? Well, because if I drop vertical lines to my line, take that distance, square it, add it all up, this black dashed line minimizes that total sum. But again, if you consider this as a simulation and you rerun your simulation, you redraw points, they are modeled as random, you will get a different line. And as saying for doing it by eye, your intercept and slope will change and they will change together. It's a function of simple linear regression that you always go through the average X and the average Y. And so that's why if I look at my confidence around my model, because my model is a function of my random observations, so my model outcome is random, you get this band wider around the edges and more narrow in the middle. Now looking at this, you see that there's an outlying point, something with a Y value of about 20. And if you look at the error estimates around this, you get this yellow band. And this yellow band, remember, I'm saying that my individual points are the line plus an error, the variance of that error, I estimate, and I get this yellow band. Now, a potential complaint about this yellow band, strangely, is it's too good. And you might say, what do you mean too good? Well, this is a 95% confidence bound in theory. There are 80 points here. You'd expect 4 of them to be outside, and the only one out is that outlier. So that's what I mean by too good, is it might be too conservative. And something you can do, of course, is to refit the model without the outlier. And doing so, then you get the dotted red line. Note my model hasn't changed much, but now my estimate of the error has changed, giving me that red band. And now, if you put the outlier back in, 4 of them are outside. I get a slightly tighter prediction interval, but my underlying model doesn't change much. Which one's more useful? And if I go to my stakeholders and say, by the way, my first model, I encompass all of my points except the outlier within my bands, versus with my smaller bands, more of them are outside. The statistics people will say, yes, of course. If you have 80 points, 4 of them should be outside, but your business stakeholders might say, no, I want to be really confident that everything fits inside. How do you trade these off? So if I quickly summarize simple linear regression, the key points are, I've had my data provided, X and Y are defined. I've decided that the functional form should be linear, and then I can have a best fit conditioned on the responses, which again, I've assumed are random. Within my model, then, there are 2 sets of noise. The parameters, which I only have estimates of, even under the assumption that there is a true function, C0 and C1. And when I get future values, they will be random due to epsilon. And I can get correlation in my model parameters, as I was saying with the swivel, that if you increase one, you tend to decrease the other, and vice versa. So what I want to stress here is that not only am I going to estimate the average response, but I also want to estimate the variance. I want to estimate how much error I expect to get in future values. Moving on to linear algebra, if I go through the simple linear regression, I can calculate C1 and C0, or my estimates of C1 and C0, I should say. And I can do that with these formulas. You can do this in a matrix version, which may seem a little bit more complex, if you will. So on the matrix version, I have a vector of my estimate of the constant and my estimate of the slope. And I have this X matrix where 1 represents the constant, it's constant, and the other column is all of my different X values for my N measurements. And so I can create that matrix, take the transpose, multiply it by the regular matrix, invert that, multiply it by the transpose of my X matrix times my Y, and that leads the estimates directly. And if you're not used to linear algebra, that may seem complicated, but it's really straightforward. Once I have my estimates, of course, I can then go through and get my predictions of my Y values by multiplying my X values times those estimated coefficients. Now, if I want to add more variables from simple linear regression to multiple linear regression, I can do that. But now, if I'm in the kind of algebraic sense where I had those nice easy formulas, how am I supposed to do this? Well, you can do it the same way. You write down your cost function, you take all your derivatives, you set them equal to 0, you solve that system of equations for all your estimated slopes and the constant. If you then change your variables though, do you need to go back and redo it all again? And how do you know whether or not how all those slopes and the constant are related? When I was talking about simple linear regression, I was saying that the slope and the intercept may change. How do the slopes here all compare? So this is one reason why it's good to go to the matrix version. So now instead of my X matrix having 2 columns, I have one for the constant and then K for all the different variables I want to have. And so this equation is symbolically the same as with simple linear regression, but now instead of having a 2-dimensional coefficient vector, I have K plus 1 with my K independent variables and the constant. And then, of course, if I want to get a prediction, I take my X matrix and multiply it by my coefficients, and that gives me all of my predictions, Y hat. So now I want to go through this example application. That's all the mathematical background about linear regression and getting the constants. Now I want to go through an example of building a linear regression model and talking about some of the auxiliary tools associated with the model. So this is SENIC data. Not SENIC, but SENIC. It looks at a study of hospital infections. Here's kind of an overview of the data. There's a data dictionary attached, so already this is better than the majority of real-world data science projects I take. So some of these names are a little funny. We've got the average daily census. This is the number of patients in hospital on average. We get the average facility services, which is a percentage of 35 different services that hospitals offer, and it tells you how many of those. But even with this data dictionary, there are some problems I have. And the first one may seem a bit glib, but it's a real problem, in that none of them are labeled Y and X. Which am I trying to predict, and which ones do I want to take as given? If I take all of them as given, then I don't need a model, I need a dashboard. And for some of them, it's hard to know which one drives the other. So for example, length of stay. Is the length of stay higher if there's a higher infection risk? Or is the infection risk higher if you stay longer? Which one drives the other? And you run into the kind of cliche of correlation does not imply causality. So which one are you trying to estimate? And which one are you trying to take as given? And this infection risk, while it seems like a powerful variable, according to the data dictionary, it's an estimated infection risk for different hospitals. Estimated by whom? Is this an existing model? Am I supposed to build a challenger for infection risk, if it's built by someone else, do I need to pay for it? Within credit risk, there's a concept of a bureau score, and you pay for it and you get information about potential customers, and it can be quite powerful, but there's a trade-off between how much information is it giving you versus what does it cost. Furthermore to that, if you are provided with a model output, it's generally against the terms and conditions to try to reverse engineer the model. So if I say I want to estimate infection risk and I have this from an external source, it may actually be against contracts to try to reproduce it. And then there's discrimination by region. This is region in the United States. One of the problems with looking at region from 1980, which is when this data were published, is that it can be a proxy for race. It can be a proxy for economic status. And so whether or not you want to say that hospitals change infection based on where they are in the United States could get problematic. And then I can build additional features, such as the ratio of nurses to patients. How many nurses are there per patient? Or vice versa, how many patients per nurse? I can look at a utilization rate. How busy is my hospital? Number of patients per beds. I can discretize these, low, medium, high, or semi-discretize them, such as the number of beds, so long as the number of beds is less than 200, and then a general flag that says, right, this is a large hospital. Discretize it from there. I can scale the variables, make them all range between -1 and 1. I can standardize the variables, subtracting off the mean and dividing by the standard deviation. And then I can go down the mathematical rabbit hole of any combination of these variables that I like, so long as they're linearly independent. And it's somewhat captivating and somewhat beautiful with a number of opportunities that present themselves, and yet patterns do emerge. And if, hypothetically, from the depths of my depravity, I came up with some variable as a composition of linear terms and sigmoid functions applied iteratively over and over again. And in spite of, or perhaps due to, the extent of my madness, it works. Would you use it? The highlight here is that business usage, which variable do you want to predict? Data understanding, where do these inputs come from? What are the costs associated with getting them? And feature engineering apply to any data science project. So while I'm talking about this from the point of view of linear regression, if you want to use deep learning, neural networks, support vector machines, etc., this is still going to be a key part of the problem. I haven't actually started talking specifically about linear regression for this data set and this problem. Now I get into the question of variable selection. So I'm going to take my variables and convert the categorical variables to dummy variables. If I have L levels, I need L-1 variables. I can have my dummy variables be 0, 1 or -1, 1. Create desired features. So here I'm taking nurses to patients, and utilization, which is the number of patients divided by the number of beds. I'm going to remove region out because I don't want something specific to parts of the United States and correlated to racial demographics in the United States. And note that if I include too many variables, I can't make things worse in terms of the sum of squared error, because if I include an extra variable, I can always have its coefficient be 0 and make it no worse than if I didn't include it. And so if I look at utilization and I have the number of patients divided by the number of beds, am I better off with that ratio, or am I better off having the two variables separately? And something nice about linear regression is you can partition the error. And so here I have a look at the sum of squares. Remember, the coefficients are coming from the sum of the squared errors. And on the left, I have both. So I have number of beds, number of patients, and the utilization rate all together. In the middle, I have the numbers. So I'm using just number of beds and number of patients separately. And on the far right, I'm using just that ratio of the utilization rate. And then the colors, the red at the top, is the error. So even after I fit my function, I still get the sum of squared error, or SSE. You'll also see it as the residual sum of squares, or RSS. And then the blue at the bottom is the sum squared of my regression, or how much is explained. Now, it's a little odd in terms of nomenclature, that you can sometimes see sum of squared error as SSE and explain sum of squares as ESS. And here I'm using that this is the sum of squares of regression of SSR. And you can talk about the error being residual sum of squares or RSS. So be careful, because the names, depending on the convention, can be quite similar. SSR and RSS are actually opposites. It's a bit confusing. Feel free to ask a question if you still don't quite see that. But looking at the explanation, the total is the same across the top. All of these stacked bars are the same height. And all I'm doing is I'm swapping between what's explained and unexplained. But the pi is the same. And if I look at utilization, well, one variable is explaining about 32. Both variables is explaining about 36, but both explain about 45. So it's not that I add them together. There is some overlap in the information between these. And that may seem reasonable, because actually utilization is defined by the other two numbers. If I look at this from a broader standpoint, here I've expanded my variable choices. I've included the full model. So if I take all the variables and just chuck them all in, I explain about 130. Infection rate, which is the best variable in a single point, or sorry, if I use simple linear regression. And it's also the data that I showed previously in my example of simple linear regression. That was length of stay versus infection rate. Infection rate is the single best, but all these things aren't additive. The performance of any individual variable depends on what other variables are in the model. And so you end up with this kind of trade-off. And if you're not careful, you can end up putting out fires and chasing your tail. And what I mean by that is you come up with a certain set of features, you scale them all, they all seem to work really well. You decide you get more information, you do some feature engineering, you add another variable. The importance of the variables you had in the model then changes, and you end up going in this circle. Now that may seem a bit cynical, but I am going to recommend doing this over and over again. The difference is it should be controlled, it should be thought out. And you're not just spinning around in circles making these changes, but that you understand there are trade-offs. There are reasons to add variables, delete variables, and it should be with clarity about why you're doing what you're doing. To that extent, there are some ways as data scientists that we say, okay, let's make some rules. When do you add variables? When do you delete them? And so you can get into something called forward regression. And what this means is I have my list of variables and I'm going to add them one at a time. And the way I've structured it is I start with nothing, that there is no explanation based on these independent variables. It's purely random based on the mean and then variations from the mean. And what I have in the graph below is starting with infection risk at the left, I add infection risk. That explains 78 of my sum of squares. And then I add nurse load, and that explains an additional 19. And then add age, and then add utilization, and then add the rate of routine chest x-rays, and then add the average facilities provided by that hospital. And I get an estimate of what those coefficients are. The minus 0.96 is the constant, plus 0.55 times infection risk, and so forth. And that's starting with nothing and going forward. I could do it another way. I could start with everything and remove variables one at a time that I don't see are interesting. And that's what I have here, that if I use the entire variable set, I explain 130. I then remove the number of nurses, which costs me only minus 0.37. And then I remove utilization. And now I've got a little bit of a concern, because I added utilization in the forward model, but I'm removing utilization in the backward model. And this may seem concerning, but this is why I wanted to discuss which is better, having the individual numbers or having utilization. If you have the individual numbers, which I've started with my backward regression, then utilization doesn't matter much. If I have neither number and I can only add one variable, then I've added utilization in the forward model. And you may think that if you go forward and you go backward, that they should meet somewhere. But that doesn't always happen. You can end up with quite different models, which is what I've done here. And if I look at the coefficients, starting with the constant, things seem a bit odd. It's not a typo. In the forward model, I got a constant of about -1. In the backward model, I get a constant of about +1. And if you look at where the models agree, you can see there are still slight changes in the coefficients. And this is what I mean by when you add different variables, you can get different coefficients, and the importance of them is different. So, 0.55 for infection risk versus 0.49 for infection risk, they're at least the same sign, but there are still differences. And so which one do you want to use? Do you want to use the forward model, or do you want to use the backward model? And looking at the rules here, you could say, well, why don't we have both? And you can. You can start off with a set of variables, and maybe you add one, and after you've added one, you revisit the importance of all of your other variables, and maybe you remove one. And once you remove that one, maybe some other variable should come in. And once you put this variable in, maybe you remove another one, and so forth. The problem here is it depends on where you start. So depending on your starting point, you can end up somewhere else. Nothing says you have to start with nothing or start with everything. You can look at it and using your own judgment or the judgment of stakeholders, start somewhere in the middle and then tweak it. And if all that seems a bit subjective or a bit hard to quantify, you can enumerate all possible combinations of the models. With this example, I've engineered, with the 2 features I've engineered and removed one, I have 11 variables, so I can build all 2,000 odd models. But if you're in a big data situation where you have 50 variables, 60 variables, it starts to get a little onerous to build all combinations, list them all. And even then, you need to decide what metric you're going to use to rank them. If you use sum of squared error, the number of variables can never make it worse, and you choose the biggest one. But I don't think that's explainable, and it might not be the best in terms of statistics. You can say you only want to include variables where the p-value is less than 0.05, to use a kind of cliche, but that's still a choice. And if you use that, note that that's not the default in a lot of stepwise regression procedures. When looking at this, you might want to look for outliers, as I did in the 1D case. And in the 1D case, I had this outlier, and perhaps using some of these auxiliary values bring it into line. Well, it doesn't. We still get this outlier up toward 20, but at least now it is the value with the highest predicted value. And a nice thing about not just linear regression, but any model is you can always plot predicted versus observed. So here I have my predictions on the x-axis and length of stay, which I've predicted on the y-axis. I can still see that outlier. But when you call something an outlier, you still have a choice about, well, what constitutes an outlier. And if this one is one, fine. Are these 2 outliers? They have other points nearby, so they don't really seem like outliers, but they do have a larger deviation from predicted than some of the others. And then you still get the choice about what do you do about it. Do you remove them and fit the model again? Do you weight them less? There are a lot of choices you can make rather than just turning the handle and sending it all through. When talking about outliers, there is this concept of a hat matrix. And what it's used for is not outliers in the dependent variable, so not outliers in y, but outliers in x. If I go back to the equation of my predicted values of y, I get that it's x times the estimated coefficients, but I can rewrite the estimated coefficients, and that's where I get this h. It's similar to the nomenclature for decomposing the sum of squared errors. You get this funny term that y hat is hat y. And the diagonal values of that hat matrix, h, is also called a leverage, or how much of each point's individual measurement contributes to its prediction. And the sum of all the diagonals is equal to the number of variables plus 1 for the constant, and the diagonals all lie between 0 and 1. So here we have a sort of constraint that I have n observations. The sum of the diagonal is k plus 1. So the average value, if you will, is k plus 1 over n. So when I talk about deviations or large values, is that in terms of the average, k plus 1 over n, or is it some absolute number? And if I look at my training data, there is one training point that has a hat value of about 0.44, and it's that one. So while most of my training data has nurse loads, that's the number of nurses to the number of patients, is between 0 and 2. This one point is out there greater than 2. And the utilization is normally between 50% and 1. And this one's well out greater than or at 0.4. So if you're going to standardize or scale your independent variables, your X variables, rather than looking at distributions of all of them, you can calculate the hat matrix and use that as an indication as to whether or not some of these points are outlying in terms of the independent variables, not necessarily the predictions. So now I'm going to move on to my test data. And what you normally see happening is you train your model and you run your test data, you look at the metric, you expect it to get worse, but you want to know if it's reasonable. Yes, but that doesn't help you in real time. If I productionize this model, I want to know whether or not I'm going to be able to use it with confidence, and I want to know whether or not its predictions are useful to me. And something I can do with linear regression is I can not only return the predicted value, but as for the simple linear case, I could get this prediction range. So here I have a lower and an upper estimate for what individual measurements should be. If you look at these, at the last one, the 14.18, you'll see that it's about plus or minus 3, a little bit more. And all the other ones are less than that. As before, for the simple case, you do get this broadening that the further you are from the average, the less confidence you have. It's not that significant in terms of the difference, but if you look, you will see that the prediction does change point to point. Or sorry, not the prediction, but the predicted variance changes from point to point. And in addition to providing this, I also want to emphasize this isn't a magic wand. You don't get perfect estimates of what all these predictions are. There is an associated range to what I expect. But that last row, that 14, that's higher than most of my training data. Can we know that? And if I have something that looks like it will be outside my training data, what should I do? Should I ignore that measurement? Should I subject it to extra scrutiny? Should I ignore my model for this last point? What should I do if I do find a point that looks suspect and makes me wonder whether or not my model is still appropriate? In terms of the coefficients of my model, the model I've built, if I were to take my training data, augment it with the test data, or pretend like that test data is all I have and refit the coefficients, what would happen? I can calculate the mean squared error, so an estimate of that error variance from my data. And the numerator there is the sum of squared errors, which remember, if I add variables, that never increases. But what might happen is the mean might go up because upon calculating an extra coefficient, I lose a degree of freedom. So while the sum of squared errors may remain, will never increase, it seems a bit odd, but if you add a variable, the mean squared error may increase due to the loss of the degree of freedom. And I can calculate the covariance of my coefficients based on that x transpose x quantity inverse. And if I do that, everything here in that covariance matrix, you can visualize the correlation between your variables. And in particular, the constant has a large variance. So while in forward and backward regression, the constant change sign, it has a covariance of about 6. So, sorry, a variance of about 6. So the large deviation of 2 is within my expected variance. So looking at this, you can start to see that my ratio features have larger variance than some of the other ones. And this is one reason why it's good to scale your variables so that they're all in similar sizes, because saying the coefficient for something of utilization, which normally ranges between 0.5 and 1, you're going to have a different order of magnitude than looking at something like average facility of services, which ranges between 20 and 60. Now I can use my hat matrix, which I used for my training data. I can use the same concept on my test data. And looking at the variables here, once again, large values of the hat matrix imply that your new data might not be aligned with your test data, or sorry, with your training data, but you still have the choice of what's large. And if you have something that's large, what do you do with it? You can default to legacy methods. You can use whatever process you were using before you got the model. And so here there's a test data point with a hat of 0.29, which looking at the same plot I did before it doesn't look like it's that different. So one thing you might want to do is investigate further. And here I've changed what variables I'm looking at. And now the 0.29 is outside the routine chest x-ray and toward the top of the average facility services. And there's another point that's low in the average facility services that has a hat of 0.19. So again, it doesn't tell you what to do. And that value with the 0.29, that's the one that's giving me a prediction of 14 days, which is higher than most of my training data. What do I do with it? But at least now I have some quantitative measure that says, hey, I expect there might be a problem here. Once you build a model, it's good to have a monitoring framework. And what I'm going to use my test data for is to assess whether or not my monitoring framework is going to work for my live data. So I haven't just calculated the mean squared error and evaluated it, but I want to generate some plots that I would use when my model is live to assess its ongoing performance. And just as I did for the simple linear regression, here I have predicted versus observed, length of stay. The value that I was concerned about with the hat matrix of 0.29 and was about 14 days, works fine as it happens. So here I have the graph. The color is training and test. Training is the greenish color, test is brown. The size is the hat matrix. So this one out here is the one I was worried about, but actually this is a bigger problem. And I didn't have any clear indication that it would be outlying as far as it is. I can look at the distribution of my hat matrix for training and test data. And I get this type of graph where I have this bump around 0.15. So my test data has shifted a little bit with respect to my training. Whether or not that's significant, whether or not that's useful, I'll talk about a little bit later. Another idea is to use QQ plots. These are a little bit more sophisticated, shall we say, in terms of the statistics of what I'm looking at, but it's the kind of cumulative distribution. And this is somewhat common, where if everything were perfectly normally distributed, it would all fall on this nice line. But in fact, I've got heavier tails than normal, so I get things that are far below. And you can see this kind of skew where it's below and then above. On my training data, my test data is pretty much uniformly below. And then looking at residuals, so this is the difference. I get my prediction, I get my observed, I take the difference as the residual. You can histogram the residuals, which I have here. Again, the colors are the same, where the green is my training data and my brown is my test data. You can do a great deal of monitoring based on your residuals. Here I just have a histogram, but you can look at it versus predicted. You can look at it over time to see if your so-called independent variables are autocorrelated. You can look at it based on omitted variables to see if you had included them, if it would make a difference. You can look at it based on your variables you are including to make sure you're not having higher order effects. According to references, which I'll talk about at the end, there's 7 different types of graphs you can look at just on the residuals. And one of the challenges for this monitoring is you want to make it as simple as possible, but no simpler. So yes, I could have graphs and metrics and everything else that makes it very hard to review. But then what typically happens is some of the metrics say everything is fine. Other metrics say your model's broken, you need to fix it. And whether or not you want to be optimistic or pessimistic takes a greater importance than the metrics themselves. So here I have a very simple monitoring where I have two of the graphs I had previously. On the left, I have my predicted versus observed, and on the right I have my hat matrix distribution. And if I look at this deviation in terms of my hat matrix, most of them occur in this lower left section of my predicted versus observed, which I've highlighted here. And I can see that there's a lot of underprediction going there, and it looks like there might be a line just in there. So can I segment these variables? If I go back and look at these variables based on their performance, can I find a new feature, or can I use some form of clustering to segment all those to be the same and build another model? So I'm not chasing my tail and looking at things, but rather I'm considering the outcomes of my model performance. I'm considering the outcomes of the monitoring, and I'm trying to use that in a constructive way to redefine my model. And secondly, for my training data, I had an outlier, and I was willing to chalk it off as an outlier. And I don't want to call 2 as a normal cluster, but what's going on is this 2 outliers that happen to lie close to each other? Is there something in common between these 2 variables? What can I find out? The data in the sample data set don't have an ID, so I don't know much about which 2 hospitals these are. But if I were to go in and start digging, can I find features that explain these 2? Can I find reasons why I should be excluding these? Can I develop rules that say, if you have a hospital that looks like this, don't use the model, do something else instead? In addition to these technical things, you also need to demonstrate the business impact. It's easy to say, well, your model gave us this prediction and there's this one case that was out. You have 2 outliers, the model is useless. What's the impact of having those 2 outliers? What's the impact of getting it right, or at least within your confidence bounds, the other 110 times? Does the benefit of that outweigh the cost of getting it wrong sometimes? And it can be hard to know. And if you're ready to launch, and someone looks at it and says, I don't like this model infection risk, you're dead. And you can run into these cases where there's a lot of talk that a lot of data science projects don't make it into production. And as a data scientist, your question should be, right, well, what are the features involved? Where do I get these features? Do I have access to these data? Where am I getting the data about whether or not data science projects did make it into production? Because analytics capability of management sounds like a nice variable, but how is it stored in the database? How is it measured? Where does it come from? What do you do to try to estimate whether or not all of your mathematics and all of your calculations make it so that you're able to make the jump from your current business process to this idea of automated outcomes? A few conclusions. So in summary, a lot of the choices you make in fitting linear regression models, and most other models for that matter, come down to choice and trade-off rather than right and wrong. Which variables do you use? How do you decide which variables to use? How do you create features? How do you engineer them? If you have outliers in your independent variables, how do you quantify that? What do you do about it? If you have outliers in your dependent variable, how do you quantify it and what do you do about it? And in my opinion, the strength of linear regression isn't about calculating this formula, because it's still bound by choices and trade-offs. But you get this idea of prediction intervals. In addition to the prediction of what outcome I expect, but I get this range idea. If my population shifts, I should be able to see that in the hat matrix. If I look at different parts, I should be able to improve my model by resegmenting it. And if I find areas where my model's not working, hopefully I can discover new features and go around that loop in a controlled manner rather than being reactive about it. Other ideas, generalized linear models. You may have heard of logistic regression. There's Poisson regression. There's a lot of different choices and a lot of different extensions you can use to linear models, which are quite small if your error terms aren't normal. It doesn't come up much in data science, but there is a whole field of so-called design of experiments. And loosely speaking, that means making X transpose X inverse as nice as possible. In particular, if you can make it orthogonal, then you remove the correlation of all of your independent variables and things get much nicer. If you're looking for an introduction to that, there's something called Taguchi methods, which is a very cookbook approach to designing your experiments. And again, while it may not happen as much in data science, if you are running experiments in a laboratory or simulation experiments, it gives you some ideas of how to set it up in a controlled fashion. Remediation, you can use iteratively reweighted least squares. If your error variance depends on predicted, you can iterate through and de-weight variables. And this is one way to handle outliers, is you reweight it and you provide less and less emphasis to your outliers, and you can build a model with some controlled format. Ridge regression, lasso, elastic net, trading those two off can help you build a model where all of your independent variables are correlated and you need to decide which one, or if you can bias your model to produce better results. And much, much more. This is my main text for learning linear regression. It's 1,000 pages. So while you may think linear regression is a simple thing, it's a very extensively studied area and can be of great value. So that's the basics behind linear regression and why I support it. And again, most of the talk is about AI and machine learning on the cloud, etc. The question or my concern is that progress is normally gradual. So there's all this talk about thinking outside the box. Actually, that's not my recommendation. My recommendation is to think inside the box and then lift the box. So get data, decide what variables are important, build a dashboard, simple linear regression, monitor it, find features that break it, multiple linear regression, and then suddenly you're willing to look at this big jump that may seem extreme at the start, but is actually the next logical step on your analytics journey. Where you can find me if you have any questions, I am an independent consultant, Doc Savage Solutions. I've got a webpage. Add me on LinkedIn, have a chat. This talk and a lot of other ones are on my YouTube channel, and you can go and find more information there. Acknowledgements. Thank you for the invitation to the AI Upskill Conference. The linear regression book I used is there. The SENIC data set is included with part of that book. And of course to Jiffy, because there's so many GIFs in so little time. And thank you all.